Hello friends, in this video we will see how resistor, inductor and capacitor individually behaves in AC circuits, and thereafter we will see what happens when combination of RL, RC or RLC is taken. Let us begin. Now we will see behavior of resistor R when AC circuit is applied, or behavior of R in AC supply. Let us assume resistor R and supply voltage is V of t, which is sinusoidal, so Vm sine of omega t. Because of the sinusoidal voltage, a sinusoidal current will also flow through the circuit. Let us assume that current as I of t. Now we will see V of t, which is Vm sine of omega t, can be written in polar form like this: V vector as magnitude, which is Vm at an angle of 0 degree. So this is V vector. If V of t is known to you as well as R is known to you, it is easy to calculate I of t just by applying Ohm's law. So by Ohm's law, I of t is V of t by R, or I can write I of t is equal to V of t that we have is Vm sine of omega t whole divided by R, or I can say I of t is simply Vm by R sine of omega t. We know the fact that what we should have here is nothing but peak value of the current. I can replace Vm by R as Im upon R. We can replace Vm by R as Im sine of omega t. Therefore, now I vector, I can write it as Im at an angle of 0 degree. So this is the value of I vector. V vector and I vector we already have. Do not forget, here Im is nothing but Vm by R. After this, we will see the next segment where we will calculate impedance, that is ZR. Means impedance of the circuit when only resistor is present. ZR is also a vector value, therefore given as V vector upon I vector. Or I can write ZR vector as, what is V vector? V vector, as you can see from equation 1, it is Vm at an angle of 0 degree divided by, and as you can see equation number 2 here, I can replace I vector also as Im at an angle of 0 degree. ZR vector is equal to, we know the fact that Im value was Vm upon R, so now we can replace Vm at an angle of 0 degree divided by Vm upon R at an angle of 0 degree. Vm will get cancelled. What ZR vector is? ZR vector is simply R at an angle of 0 degree ohms. This value of Z, that is nothing but ZR, is R at an angle of 0 degree. It is nothing but a polar value. We generally represent our impedances in rectangular value. So we can rewrite this ZR vector as R plus J0. So this is a standard way to represent impedance. Now we will see impedance diagram. Impedance diagram means right now we have ZR as simply R at an angle of 0 degree. That is ZR vector is R at an angle of 0 degree. I can actually draw a vector like this. That is R at an angle of 0 degree. That's it. This is what we call as impedance diagram. That is drawing vector of the impedance. After this, we will have vector diagram now. Vector diagram means, first of all, we will draw V vector. If you remember, V vector was Vm at an angle of 0 degree and I vector was also Im at an angle of 0 degree. What does that mean? Voltage vector and current vector are in the same phase, which is 0 degree. So I can represent I vector here. As you can see, both of them are sharing a same phase, that is common phase, that is 0 degree. So if I ask you, what is the phase difference that you get between voltage and current, what should be the answer? Since they are in same phase, there is no phase difference. It means phase difference equal to 0. So 5 means phase difference is nothing but phase difference between V and I is 0 here. Then we calculate power factor. Power factor is given by formula cos phi. Since phi is equal to 0 degree, I will say it is cos of 0. We know the fact cos 0 is what? 1. It means power factor is equal to 1. This is what we call as a unity power factor. Right? So what we have studied in R, let us summarize it. So the summary is V vector and I vector are in same phase. Meaning that phase difference is equal to 0 degree. Therefore, we always have unity power factor in resistive circuit. Secondly, we can implement ZR vector as R at an angle of 0 degree ohms. In which form? Of course, it is polar form. And we can represent same ZR vector as R plus J0 ohms in rectangular form. This is about R. Let's go for inductor now. Let us assume inductor in henries, which is supplied with AC voltage source. As usual, let's say V of t, which is, let's say, Vm sine of omega t. Because of the sinusoidal voltage, sinusoidal current will flow through the circuit. Let's say it is I of t. There is a popular relation between V of t, I of t and L, that is nothing but voltage equation for inductor. I'm sure you remember VL is L into di by dt. Is that right? Using this relation, now I will say V of t is nothing but L times d by dt of I of t. In this case, V of t is known to me, I of t is a question mark, so I can also rewrite the same relation as I of t. I will integrate on both the sides, so I'll get 1 upon L integration of V of t dt. Or I can represent I of t as 1 upon L integration of V of t is what? It is Vm sine of omega t dt. Am I right? Let's have this integration. I of t is equal to Vm is a constant part, will come out, divided by L, as well as sine omega t integration is minus of cos omega t. So it is minus of cos of omega t divided by constant, which is omega. I can rewrite this I of t as minus Vm upon omega L cos of omega t. We know that minus cos omega t can be replaced with sine of omega t minus 90 degree. So I can represent again I of t as Vm upon omega L. I am replacing minus of cos omega t with sine of omega t minus 90 degree. Sine of omega t minus 90 degree. In fact, now I can write I of t as, we know the fact that if it's a sinusoidal signal, what we always have here is a peak value. In this case, it is a current equation. I should say this is nothing but Im sine of omega t minus 90 degree. Now, from V of t, which is nothing but this equation I am talking about, we can write V vector, which is Vm at an angle of 0 degree, and I can write I vector as, from second equation, as Im at an angle of minus 90 degree. So now we will see what happens when we actually use this V vector and I vector. Now we will try to get impedance ZL. So ZL vector is nothing but V vector upon I vector. We can substitute values as V vector as Vm at an angle of 0 degree divided by I vector as Vm upon omega L at an angle of minus 90 degree. I can cancel Vm and Vm here, so ZL vector it's simply omega L at an angle of positive 90 degree. Because in polar form, in division angle gets subtracted, so it is 0 minus of minus 90 becomes positive 90. Secondly, I am sure you remember in original form V vector was Vm at an angle of 0 degree and current was Im at an angle of minus 90 degree. Only thing is I have replaced Im with Vm upon omega L in this case. Finally, we have ZL vector as omega L at an angle of positive 90 degree. In fact, we replace ZL vector omega L as XL at an angle of 90 degree, where XL is called as inductive reactance. And of course, unit is ohms because it has derived from the relation V by I. Finally, ZL vector is XL at an angle of positive 90 degree. Ohms, it is in polar form. I can rewrite in rectangular form as 0 plus JXL. So this is also ZL but in rectangular form. This is also ZL but in polar form. Now we can have impedance diagram. Impedance diagram means drawing impedance of inductor which is positive JXL. So I can actually take this as a reference. Since it is XL at an angle of 90 degree, at 90 degree I will draw one vector and I'll call that vector as ZL vector. To draw it appropriately, again we take this reference and this is nothing but your ZL vector. This is 90 degree. Now we will see vector diagram. Vector diagram means drawing final V vector and I vector. For that we need to recall what was V vector and I vector. V vector was simply Vm at an angle of 0 degree and I vector was Im at an angle of minus 90 degree. Let's draw this. Suppose if I start drawing V vector which is having a phase equal to 0 degree, I can draw V vector like this, whereas as you can see current is giving you minus 90 degree phase. Minus 90 degree means I have to draw over here. Remember, if it would have been plus 90, I would have drawn I vector at upper side. The phase angle is 90 degree. We need to conclude something out of it. Do you find V vector and I vector are in the same phase? Answer is no. As we can see, this negative phase indicates current is lagging, and by how much angle it is lagging? By 90 degree. So we say that current lags voltage in case of inductor by 90 degree. In short, phase angle, that is phase difference between V and I, is equal to 90 degree. After this we calculate power factor. Power factor is given by cos phi. That is nothing but cos of 90, and cos of 90 is 0. This is called as 0 power factor. Now we will summarize inductor, how it behaves in AC circuit. In case of inductor, current always lags voltage by 90 degree. So first and very important conclusion is that current lags voltage by 90 degree, or you can say voltage leads current by 90 degree. Both the meaning are same. Or voltage leads current by 90 degree. Phase angle is equal to 90 degree. Therefore, it gives you 0 power factor. Third, ZL vector is nothing but XL at an angle of positive 90 degree, or in rectangular form you can write it as 0 plus JXL. Of course, the unit is ohms in both the cases. So this is the summary for inductor, how it behaves in AC circuits. Let's move to the capacitor. Let us assume capacitor C in farads, to which AC voltage source is provided, that is V of t, having value as Vm sine of omega t. Because of the sinusoidal voltage, sinusoidal current will start flowing through the capacitor. Let's say it is I of t. So in first case, your V of t is Vm sine of omega t, by which I can calculate V vector as Vm at an angle of 0 degree. Now, if V of t is known, if capacitor value is known, it is easy to get I of t by using a popular relation called as current relation for capacitor, which is nothing but I is equal to C into dVc by dt. This is a standard relation by which we calculate current through the capacitor if voltage across capacitor and the value of capacitor is known to us. So now I can write I of t, because this is what we have to calculate, as C into d by dt of V of t. Because V of t and capacitor C is known to us, I of t can be written as C into d by dt of V of t. And what is V of t? It is Vm sin omega t. I can write I of t as Vm into C. Vm we have to take out. Derivative of sine is cos. So it becomes cos of omega t multiplied by constant omega. In fact, I can now write I of t as Vm into omega c cos of omega t. We always have a tendency to represent current as well as voltages in terms of sign. Let us convert cos of omega t into sine. So cos of omega t can be replaced in case of sine as sine of omega t plus 90 degree. I of t is omega c times Vm sine of omega t plus 90 degree. Again, since this is I of t and it is in sinusoidal form, this first part can be considered as peak value of current. So I can represent this as Im sine of omega t plus 90 degree, or I can now have I vector as Im at an angle of positive 90 degree. So as you can see, equation number 1 gives you V vector and equation number 2 gives you I vector. Now we will calculate impedance for capacitor. ZC vector is nothing but V vector upon I vector by Ohm's law. ZC vector is V at an angle of 0 degree, whereas current we have got omega c times Vm, or current we have Im at an angle of 90 degree. ZC vector can be written as Vm at an angle of 0 degree divided by, if you remember, Im was Vm times omega c at an angle of 90 degree. Here Vm will get cancelled. So the remaining is ZC vector is 1 upon omega c at an angle of minus 90 degree. Or ZC vector can be written as xc at an angle of minus 90 degree, where we have actually replaced 1 upon omega c with another value xc. What xc stands for? It is nothing but capacitive reactance, and unit is what? Ohms. Finally, I can represent ZC vector as xc at an angle of minus 90 degree. In what form? Of course, polar form. Or I can represent ZC vector as 0 minus jxc ohms in case of rectangular form. Let's see how voltage and current will be related by using vector diagram. For drawing vector diagram, that is nothing but drawing V vector and I vector together, we should recall V vector. It was Vm at an angle of 0 degree and I vector as Im at an angle of positive 90 degree. This is volt, this is ampere, of course. Now with this, I am asking you whether do you find voltage and current are in the same phase? Answer is no. As you can see, V vector is in 0 phase, I vector is in positive 90 degree phase. It means if I compare, this positive 90 degree indicates leading, negative 90 degree indicates lagging, or any negative phase indicates lagging phase, any positive phase indicates leading phase. It means I can now say that current I leads voltage by 90 degree. Now by drawing V vector, we should draw V vector as it is, because it is in 0 degree phase, whereas current I vector, as you can see, it is leading by 90 degree. So leading by 90 degree, so it will come at this side. This is 90 degree. Finally, if I ask you what is the phase difference is 90 degree. That is phase difference between voltage and current. With this, now we can calculate power factor. Power factor is given by cos phi, and phi is 90 degree, so it becomes cos of 90, which is again 0. So like inductor, even capacitor gives you 0 power factor. Let us summarize capacitor, how it behaves when it comes to AC circuits. In case of capacitor, we have seen first, current leads voltage by 90 degree. Second, we have seen phase difference is 90 degree, means power factor is equal to 0. Third, we have seen ZC vector is written as XC at an angle of minus 90 degree in polar form, or you can write it as 0 minus JXC ohms in rectangular form. I am sure you have understood the resistor, inductor and capacitor behavior in terms of AC circuits. Thank you.